Ladies and gentlemen, I wanted to thank you all to come, that you came after lunch. My name is Carl Glittenberg. I will be giving a presentation on advances in swept source OCT and swept source OCT angiography. Now, a little bit to my background. I'm a medical retina specialist, and I worked for many years in the Karl Landsteiner Institute for Retinal Research and Imaging, where I'm still affiliated to it. Where I did a lot of research on three-dimensional visualization and showing and adapting data from three-dimensional OCTs, from intraoperative OCTs, so on and so forth. For about a year now, I've been the senior clinical advisor and the senior manager for global medical affairs for the Topcon company. And as such, I have an obvious financial disclosure to give here, being a full-time employee of the company. But this presentation that I'm giving today is not so much about what is directly possible on the machine right now, although all the data that you will see here was collected using the commercial machine, but it's more about what's going on or what is possible to do with the data sets and some of the research that I've been doing, visualizing what's possible to do using swept source OCT and swept source OCT angiography. So let's start with swept source OCT. If you look at the speed increase over the last decade or so, or the 2 decades actually, since the Zeiss OCT 2000 started around 1996, you see an exponential speed increase. And right now we're at about 100,000 A scans per second using the swept source OCT. So that gives you an incredible amount of speed that you can use to collect a very large amount of data. And that large amount of data is what I'm going to be showing you today, what we can use, that we can use in a very, very interesting way. Additionally, you can see that using a traditional 840 nanometer wavelength in comparison to using the 1050 nanometer wavelength that is used in swept source OCT, you can see that there is a lot more deeper penetration using the 1050 nanometer wavelength because there's a lot less signal roll-off that you would have in the 840 nanometer wavelength. This means you have a lot deeper penetration when it comes to cataract, when it comes to uveitis, when it comes to hemorrhaging, which you can, for example, see in this patient right here. Here you can see, even though that there is a subretinal hemorrhaging, you can see that there's penetration right through the retinal structures, right through the RP, right through the hemorrhaging, all the way through the choroid, all the way to the choroidal scleral interface. And that is very, very important in some of the future slides that I'm going to show you, because only using this wavelength can we get the imaging that we're trying to achieve. So let's start with 3D swept source OCT. As I was saying, one of the things that I was looking at was taking this very, very dense amount of data and seeing what could be visualized using that amount of data. So here you can see a vitreomacular traction syndrome. And as said, this is, in this format, it's not commercially available yet, but it shows what kind of data you can collect using the commercially available system. So here you can see a vitreomacular traction syndrome. You can see the retina. You can see the posterior hyaloid pulling up the retina. But what you can see in this visualization is because in the program that I wrote, I correlated the reflection intensity of the OCT scans directly to the transparency in the visualization, meaning that the less transparent it is, the higher the reflection in the A scan. So in other words, theoretically, this would correlate to the density of the reflection, which means the density of the collagen fibers. So in this kind of situation, you could look at this visualization and glean information about whether this patient would be receptive to treatment with ochreplasmin, because you have a very, very small adhesive area and you have a very, very, not a very dense, dense adhesion. In comparison to this patient, who has a very dense adhesion in 2 areas. So he has a vitreomacular and a vitreomacular and vitreopapillary traction in this patient with the uveitis. And you can see that the density of the adhesion is much denser than the previous scan. So you wouldn't use ochreplasmin in this kind of patient. Of course, you wouldn't use ochreplasmin in this kind of patient anyway, because it's a posterior uveitis patient. But what's also very important here is that you can see each and every inflammatory cell floating above the retina. So what I'm trying to work on is a method to get this kind of data and to get an objective cell count of inflammatory cells in posterior uveitis, which would be something that would be very, very good for uveitis treatment to get an objective cell count, since we all know how subjective cell counts are at this time. But it can be also used in a different scenario. This is a patient that came to my clinic with a stellate non-hereditary idiopathic foveomacular retinoschisis, or a sniffer patient. And as you know, these patients sometimes have a relatively high visual acuity, and I wanted to know why, because I saw there's a strong retinoschisis, and I was very surprised about the visual acuity. But you can see the Mueller cells as they're being stretched upward. And I wanted to understand this better, and I wanted to see if with the dense data set, is it possible to understand this disease better? And yes, it is. So if you do an OCT angiography and you look at the structural data, you see the stellate structure of the retinoschisis very, very clearly. If you put it through my three-dimensional reconstruction program, you clearly understand the structure much better. Now, what we want to do in future is in studies to try to see if we can correlate in the hereditary forms the phenotypes with the genotypes, so that we can, in the future, when it comes to gene therapy, get a better understanding of which phenotypes respond better to genetic therapy. And that, again, is just a way to visualize how dense the data is and how much information you can receive with this data set. Now let's go to swept source OCT angiography. This is my right eye that I visualized using a fundus photo, and I'm just going to show how we get an OCTA of this vessel. So we go over it 4 times. Then we take all of those 4 scans, and we get scans of erythrocytes and of the structures around it. We do a subtraction analysis, and then we get a picture of the moving erythrocytes. And then we get an OCTA from that. Now, that's not very, very clear, and I was in Rome in an OCT angiography meeting, and I realized that this wasn't very clear, so I went to the Trevi fountain. Sorry. So I went to the Trevi fountain in Rome, and I did a video of it, and I wanted to do an OCT angiography of the Trevi fountain in order to visualize it. So what we want to do is we want to remove all of the not moving statues and keep all of the moving water. So you copy the film. In the copied film, you remove 2 or 3 frames, and then you copy the first film from the second film, and what happens is this. So this is an OCT angiography of the Trevi fountain, and when you sum it, you get this. So here are the larger vessels, and here are the smaller vessels. So all in all, what you do is you remove, when you do a subtraction analysis, everything that is the same in the 2 frames gets subtracted, and everything that is not the same in the 2 frames does not get subtracted. So that's how you end up with this visualization. Now, using that, you can then visualize OCT angiographies of different pathologies. So here you've got a choroidal neovascularization with some SHREM, some subretinal fluid, and inside the SHREM you can see very, very clearly this neovascular membrane. And you can see the flower shape of it, you can see the C-fan shape of it, you can see the anastasmosis, you can see the curls, you can see that this is an active lesion according to the criteria by Koskas. But I had a discussion with Professor Koskas regarding the fact that these activity criteria were based on a 2-dimensional image. But the actual lesion is 3-dimensional. So what I worked on was a way of segmenting the choroidal neovascularization 3-dimensionally and giving it a 3-dimensional triangle mesh segmentation so that we can then use it for fluid dynamic simulation and volumetric analysis, and then really start to get much better understanding of the activity criteria, so that we don't have to do 3-dimensional fractal dimension analysis, which is extremely complicated. If we can do it in this way, we can save ourselves a lot of computational time and also spare our artificial intelligence. Now, it's also possible, of course, to do OCT angiography of the optic nerve head and look at this, for example, this neovascularization of the disc. So here you have a proliferative diabetic retinopathy with a neovascularization of the disc, but there was more information in this image that we weren't looking at, just looking at the OCTA. You also had the OCT-B scans, which showed a vitreopapillary traction. Now, I had in previous studies shown that there's a correlation between vitreomacular retraction and choroidal neovascularization. And I wanted to see with this animation if there is a correlation between neovascularization of the disc and a vitreopapillary retraction, to see if there's a direct correlation. So if we overlay the two images, you can see that these tractive membranes right here point right here. And if we take this out, you can see that there's a direct correlation between the neovascularization of the disc and the tractive membrane. Also, on the other eye of the same patient, we've got a subhyoidal hemorrhaging. You can see right through the subhyoidal hemorrhaging because of the wavelength all the way to the choroidal scleral interface. And you can even then get a usable OCTA, which is again due to the wavelength being used. Also, but of course, if you want to do real screening for ischemia, you need much larger scan areas, so it's possible to get mosaic scans up to 20 by 20 millimeters so that you can really scan for ischemic areas in branch retinal vein occlusions or diabetic retinopathy. So let's skip this because of time. So let's go to the second part of the presentation, which has to do with choroidal vasculography. It's not possible to do an OCT angiography of the choroid for this reason. If you have a light here and it shines through here, it'll throw flickering shadows on everything beneath it, right? So if you have here the light source, you'll see this flickering on the RPE. And because the choriocapillaris is a very, very dense group of vessels, it throws projection artifacts on all structures beneath it, which means you can't get an OCTA. But if you look at this very closely, this image right here, you can see that all of these vessels here in the choroid and in Sattler's layer and in Haller's layer are black. Now, why this is an OCT is not very, very clear. There have been some theories in Phil Rosenfeld's group that say that this might be due to forward scattering of the signal instead of backward scattering as soon as the light passes the RPE. And this would actually show that because you see that there are forward scattered light beams here next to these choroidal vessels. But regardless of why this happens, this can be used to do something I call choroidal vasculography. And in order to show that, I have this patient who had this weird choroidal vessel that was protruding, and it was due to a scleral bulge. And I wanted to see if I could visualize the choroidal vasculature around the scleral bulge. And as you can see, what I did was I did an OCT angiography and used the ANFAS information from the angiography in order to see if it was possible to directly visualize this vasculature. And what we can do is we see here the OCTA, and here we see the ANFAS OCT, and this is a 26 micron slab based on Bruch's membrane that you can then move up and down, right? And what happens then, if you move it up and down, you can flow through the entire choroidal vasculature, just like you can in OCTA. But I want to really point out, and this is very important, that this visualization does not show the movement of blood. It just shows the vessels around it. And since it's not showing the movement of blood, I call it not angiography, but vasculography, because it's showing the vessels. So I've called this choroidal vasculography, or CVG for short. Now, of course, the first time I showed this, people were going like, okay, yeah, that's very interesting. You're showing artifacts and you're calling it names. So I took it to my patients and I compared it to ICG, the gold standard. And if you look at the ICG here, and here you've got the choroidal vasculography, this is in different depths in the choroid, but if you look at all of these vessels, they're all to be found again in the ICG. So this isn't something that is being made up by the system, these are real structures. But just like OCTA, this technology cannot show leakage, but it does give you a lot of information. So again, you can flow through the entire thing, you can see all of the vessels, you see Sattler's layer, you see Haller's layer, and you see parts of the choriocapillaris, and you see them all the way down to the choroidal scleral interface. So this can give you a tremendous amount of information. Again, here we have another case of a patient with a CSCR and with a secondary CNV. So in the ICG, you barely see the choroidal vessels at all. But in the CVG, you see in the different layers all the choroidal vessels in very high detail. Again, you don't see the leakage, but you see the choroidal vessels. Now the question is, what's the purpose of all this? If I can't show leakage in the choroid, why am I trying to visualize it in the first place? Now there are a lot of diseases, both systemic and local in ophthalmic diseases, that end up in either a thickening of the choroid or a thinning of the choroid. But up till now, we just define pachychoroid, or we define the thinning of the choroid, but we're not saying where it's thinning. We're not saying, is it thinning in the Sattler's layer? Is it thinning in the Haller's layer? Is it thinning or thickening because of the vessels thickening, or is it thickening because of the stroma thickening? So just measuring the choroidal thickness isn't going to work. So we need to look at the differences between the different layers of the choroid, and we need to see the relationship between the vascular changes and the stromal changes. And this can be very important in, for example, Alzheimer's and in Parkinson and multiple sclerosis, because all of these things change the way this vasculature is structured. So here, I create a three-dimensional representation, and you can see these vessels right here. That's Haller's layer, and this whole thing is seen from the bottom, so you see some vessels under Haller's layer that are small and crossing over Haller's layer, which is something that we hadn't visualized before. So you can segment it again, and you can visualize it very, very clearly. It's sort of like a cast that we used to do, but in this case, you of course don't have to sacrifice the patient. So you can see exactly what's going on inside the choroidal vasculature of a patient that you really have in your office. So let's go back to this patient with a scleral bulge, and you see this little squiggly vessel here, and I wanted to see how far can I visualize it. Now what you're about to see now has no clinical value, but I wanted to do it as a proof of concept. So I took that data set and I segmented it in the three-dimensional segmentation, again so that we can get a difference between stroma and vascular structure, so we can really visualize it, but also so that we in future perhaps can use this for fluid dynamic simulation and volumetric analysis and artificial intelligence analysis. But I wanted to get even closer than this to the vessel. So I took that vessel and I wanted to see how close to the vessel it's actually possible to come using data from an actual patient. So it's obviously possible to get very close to this patient. So again, you ask me, what's the point of getting this far inside the vessel? The point is, it's segmented. All these walls have a triangle mesh. I can give them physical properties. I can give them simulation properties. Because in the software that I'm using and that I'm working on, it's also possible to do fluid dynamic simulation. So this is a simulation I created of blood flow, just to see, as a proof of principle, to see if I could correctly simulate blood flow. And I wanted to see if I could take this information of, with the viscosity and all of these formulas, and see if I could plug this directly into the vessels I'd segmented before. And it's possible. So you can do a fluid dynamic simulation of the actual vasculature directly of the patient that you're seeing. Now this is of course not possible on the machine, but it shows you what's possible to do with the actual data that's coming out of the machine. So this is some of the work that I'm working on in the future. With that, I wanted to end my presentation, but I wanted to invite you all to the second International Swept Source OCT Angiography Conference, which is in the 16th and 17th of February in Paris. The first one this year in February was very, very well attended. We had 400 attendees and some absolutely great speakers with Rick Spade, Vasada, Jim Fujimoto, and so on and so forth. And we would love it if you all came to this meeting. Thank you very much for your attention.